Section 3.2 is polynomial functions and their graphs. So the first thing we're going to talk about is end behavior. And we have 4 graphs on the right, and we're going to figure out what we notice about the graphs of each of these functions with specific characteristics. So if I look at the first one, I have an odd degree, and it's a positive leading coefficient. And as x goes to positive infinity, so as I go to the right, y, or f of x, goes to also positive infinity. And then as we go to the left, the function goes down towards negative infinity. Now, something to note, the in-between right here, this is just, this is just intended to be a graph that shows the end behavior. Don't worry about the fact that there's points and it looks like a V. They all pretty much look the same. So ignore the middle section. We're strictly just looking at the end behavior. All right, so for B, if we have an odd degree and a negative leading coefficient, as we go to the right, the function goes down. And as we go to the left, the function goes up. Then if we have an even degree and it's a positive coefficient, both ends go up, and an even degree, but it's negative leading coefficient, both ends go down. So this holds true, this end behavior holds true for polynomials. So the first thing we want to do is say, okay, is it even or odd? If it's odd, they're going to end in opposite directions. And then how do we know if the left goes up or down or the right goes up or down? It depends on the leading coefficient. Is it a positive number or is it a negative number? Then for even functions, notice that they both end up or both end down. So again, if it's positive leading coefficient, both ends are going to end up. If it's negative, both ends are going to end down. And then at the bottom of that sheet that you have, it says, note that the graphs of a polynomial function are always going to be continuous and smooth. So smooth and continuous, smooth and continuous. It's not going to be piecewise functions. You're not going to have to lift up your pencil if you're tracing it. Okay, so there's a relationship between the number of turning points, so like a peak or valley, a turning point, and the degree of the function, and this is it. A polynomial of degree n has at most n minus 1 turning points. So if we have a degree of 5, for instance, we're going to have at most 4 turning points. It doesn't mean we're going to have 4. It just means it can't be 5, 6, or 7. So it can be anything less than that, but at most it's going to be n minus 1. So based off of what we found before with end behavior and now turning points, we're going to sketch a graph of the possible polynomials that are going to have a degree. We'll do the first one. So A says a degree of 5 and a negative leading coefficient. Okay, so here's my graph. If it's a degree of 5, it means it's an odd degree. So for number 1 on that paper, we're looking at part A and B. Since it has a negative leading coefficient, that means as we go to the right, it's going to end down. And as we go to the left on the x-axis, it's going to end up. So I can have now at most 4 turning points. So I can have 1, 2, 3, and 4. And notice how it connects with what my end behavior was. Now, I don't have to have 4 turning points. I could also show the same thing. We end up on the left and down on the right. I could have maybe just 2. However I can connect those 2 is how I can depict a degree of 5 with a negative leading coefficient. So if we have a degree of 6 and a positive coefficient, we have 3 possibilities. So a degree of 6, which means it's even, so it's either both going to end up or down. Since it's positive, both ends are going to end up. So I can have 5 turning points. And that would look like this. 1, 2, 3, 4, and 5. Or again, both ending up. I could do 1, 2, 3, stretch that out, 3 turning points, or I could also have no turning, or just 1 turning point, like this. Now we're going to talk about the number of zeros and multiplicity. So, what do you notice about a degree of the function and the number of zeros? A polynomial of degree n has, at most, n zeros, or x-intercepts. So now we're going to talk about what is happening at the x-intercept. So any function that has a multiplicity of 1 is going to go straight through the x-intercept, or x-axis, I'm sorry. This is going to be our x-axis. So it could go like this, or it could look like this. Now, if we have a multiplicity of 2, at the x-intercept, we're actually going to bounce. So we touch it and come back up. This is a multiplicity of 2. So I can, it's quadratic essentially, but the whole polynomial might not be quadratic. It's just like if you covered up part of the polynomial at this point around the x-intercept, it's going to look like a quadratic shape, like a parabola. So that means it can also bounce and go down. And then if it has a multiplicity of 3, through the x-axis, it's going to kind of do like an S snake, or like a curve like this, one or the other. Okay, so now we're going to look at the 4 polynomial functions that are in factored form and compare them, or match them up with the 4 graphs at the bottom. Now, they all have the same value for zeros, but we're going to start looking at the end behavior and the degree and multiplicity to see if that, to be able to match the function in factored form to our graph. So if we look at this first one, then this bounce that we have right here, okay, now I fixed my paper. Okay, so this bounce that we have right here and right here, they both hit and go down. So this tells us we're going to have an even degree. Okay, we don't know if it's going to be 2, 4, 6, but we know it's definitely even. And then at this x-intercept, that has that S-shaped curve, so that means it's going to be odd. Okay, and again, that's for the multiplicity. So if we look at the function, we need to see at x plus 2, we need an even number. So we're only looking at c and d. And then at x plus 1, we also need an even degree. And c is our answer here. And then that confirms that at x minus 1, we have an odd degree because it's 3 in the function. Okay, so looking at the next graph, right here, it goes straight through, so we have a multiplicity of 1. Our second x-intercept is going to be even, because it does that bounce and goes back down. And then our last one's going to be odd, because it has that S curve to it. So at x plus 2, we don't want to see a degree, so that's going to be either A or B. And then at x plus 1, we want a 2, so that means A. And then that confirms that at x minus 1, we have an odd degree, which is 3. So this one is A. Okay, next function. The very first one we have to the left is going to be even, because it hits and goes back down. The next one's 1, because it goes straight through, and our last one's going to be odd. And that follows with D, function letter D. And our last one we know is going to be B, but let's just confirm. B does have a 1 degree on x plus 2. It does have a 1 degree, or a degree of 1 on x plus 1, and then it does have an odd degree at x minus 1. So now we're going to go backwards, and given the graph, we're going to determine the degree and the multiplicity, and then we're going to actually write an equation, and we can write it and keep it in factored form. So the first thing I'm going to note is that we have a multiplicity of 1 right here, and our second one is going to be an even multiplicity. Now, we don't know if it's going to be even as in 2, 4, 6, 8, so we're just going to stick with 2. Now, what that means, though, is that we have y equals our factors, our x-intercept is 1, so our factor is going to be x minus 1. And then our next one is 4, so it's going to be x minus 4. And since it does that bounce back up multiplicity, it's going to be x minus 4 squared. Now the next thing we need to check is the end behavior, because that's going to tell us if our leading coefficient is positive or negative. So we know it's odd because both end behaviors are in different directions, and since we end, or on the left it goes down and on the right it goes up, that means it's positive. So we don't even need to write anything. This is our equation for our first graph. Now for our second one, the first multiplicity, well, actually looking at all of them, they all have a multiplicity of 1. 1, 1, 1. They all go straight through. So that means I'm going to have y equals, now it goes through, I usually write x first if we have one that goes through 0, 0. So that would be x plus 0 or x minus 0, which is just x. So we have x times, and then we have a factor at negative 1, which is x plus 1. And then we have one at 3, which is x minus 3. Now, if you look at A and B, they're both odd, but their end behaviors are in different directions. So since this one starts on the left, it goes up, and on the right it goes down, that means it's a negative leading coefficient. So I'm going to put a negative right in front of that x. So that is our function in factored form for our polynomial. For C, we just have one multiplicity of 2, or even, because it hits and bounces. So that's only going to be one factor. Since it's at 1, it's going to be x minus 1. Since it's even, we're going to write 2 because it hits and comes back down. And since we know parabolas pretty well, it opens down, so it's going to be a negative in front. But also with multiplicity, since it's an even degree, which is 2, then that means both ends are either going to end down or up. And since these both end down, that means we have a negative in front. And our last one over here, it goes through 0, 0 once, and it goes through 2 and has an odd multiplicity. So since it goes through 0, 0, that's just going to be x, and it goes through 2, so x minus 2, and odd, we're going to write 3. Again, we don't know if it's 3, 5, or 7, but we always write the lowest possibility, so we have 3. Since it's an even degree, because they both end behaviors are in the same direction, and since they're both going up, then it's a positive leading coefficient. So this is our final equation. Okay, and the last problem of the day, we're going to sketch the graph given that factored form polynomial equation. We're going to use our end behavior, our x and our y intercepts, and the knowing about multiplicity to graph it correctly. So the first thing I'm going to do is draw out my coordinate plane, and I'm going to go to 3 on each side. I know I'm not going to have a factor that's greater than that looking at my equation. Okay, so again, looking at my factored form equation, I know I have an x-intercept at negative 1. I know I have one at positive 1. And I know I have one also at positive 2. So I'm going to do end behavior next. So if I look up here and I count the degrees on each of these factors, if it's odd, if it adds to an odd number, it's odd. degree. If it adds to an even number, it's an even degree. So we have 1 plus 2, which is 3, plus 3, which is 6. So this is an even degree polynomial. So that means both end behaviors are going to be going in the same direction. Since the leading coefficient is positive, they're both going to end up. So sometimes I even draw my end behavior before I even draw the middle. I'm not there yet. Okay? So the next thing I want to do is figure out my y-intercept. And my y-intercept, basically, you just plug in 0 for x. So we have y equals -2 times -1 squared times 1 cubed, and this gives you -2. So at -2, I have a y-intercept. And the last thing you need to know is multiplicity. At, let's see, at +2, it just goes straight through. Then my next one at 1, it bounces, so it's going to go up, back down through my y-intercept, and then at that x equals 1, it's going to do that snake curve. And I'm actually going to erase my end behavior and do it a little bit better over here. So it's going to do that S curve, implying odd multiplicity. So there we have it. There's our graph.